I work in Hawley as the principal digital applications developer. So let's go on to the first part. So this is the agenda that I'm going to go through. So I'm going to start with, just tell me that there's a bit of lag. Let's just see, make sure it's working fine. Yeah, so let me know if you can't hear me properly. But I'm going to start with a bit of context on the construction industry and Hawley's role within it. And then I'm going to go on to the good stuff, all of the Neo4j stuff that we're working on in terms of a web app that we've built and implementing the data, the graph data structure in Neo4j. And also after that, I'm going to go on where we are planning to take it. So we are kind of building a microservices architecture type thing, and we are using GRANDstack and GraphQL. So I just go through what we're doing with that. So in terms of learning objectives, hopefully from this class, you will at least get an insight into the building services industry. But we've got quite a diverse range of people here. So some of the stuff maybe you already know, but hopefully you'll at least get information on hosting Neo4j and functions and the web app in Microsoft Azure, some information on using the Neo4j driver in C#, and of course, as I mentioned before, GraphQL and GRANDstack. So the bit of context bit. Okay, yeah.
Well, sorry to interrupt you. Something went wrong with starting the webinar, so I'll have to restart it again, and you would have to start from the beginning. Is this okay? Or...
Okay.
I'm sorry.
Yeah.
Just
no
a second. Start webinar.
Let people in.
Okay, so we're letting people in now. So let's see if this works now. So I don't know what went wrong. Perhaps I pressed the wrong button somewhere. So let's see. Okay, and now let's see, recording. Now it works. Okay, cool. So now you can go ahead and start.
Okay, so hopefully everybody can hear me fine now. So thank you for coming to my talk on graph data for the construction industry and modeling heating, ventilation, and electrical and other building services. So my name is Will Reynolds. I am the principal digital applications developer for Hawley. So in this talk, so the agenda, I'm going to go through a bit of context, first of all, just to make it clear about what exactly it is we're doing. So I'm going to go through the landscape, the construction industry landscape, and where Hawley sits within that. And then I'm going to go on to the good stuff, all of the technical stuff about how we are using Neo4j and the graph data structures that we're building. And then, yes.
You might want to re-share your screen. Currently it says only loading for me and not showing your screen.
Okay.
But at least all attendees are there now. So
yeah, well, it says that screen sharing is on. So let's try switching it back. So you seeing?
No, it's great. Cool, thank you.
That?
Yep, all good. Go ahead.
Okay, right. Yep. So in terms of learning objectives, hopefully from this class you will get an insight into the building services industry. I know we've got quite a diverse range of people in terms of abilities. So hopefully you will at least get something out of the stuff we're doing in C# and using the Neo4j driver, and also hosting Neo4j and functions and the web apps in Microsoft Azure, as well as the stuff we are doing with GraphQL and GRANDstack. Okay, so these are just some information that I looked at, that I found on Google about the construction industry. So I think it's one of the biggest industries across the world. But one of the main issues it has had is with poor productivity. So it's a huge potential for growth, and one of the main areas driving that growth is adopting new technology, so we can do things cheaper, essentially, with less staff. And so let's move on to the next bit. So I mentioned that the construction industry is in the midst of radical change. So a big driving force for that is building a sustainable future. So that's with the increasing population of the planet and the squeeze on energy supplies. We need to find ways of building buildings which are much more sustainable and use less energy and are more suitable for the people who actually use those buildings. So part of that is BIM. So introducing BIM. It stands for Building Information Modeling, which is kind of something which the construction industry has adopted over the past 10, 15 years. So essentially that is just about adopting new technology. So it's about building buildings in 3D and everybody working together in the same model. So in terms of Hawley and our role, so we do the mechanical, electrical, piping or public health services for buildings. This particular one that you're seeing was a hospital in Liverpool. So we design all of the medical gases, all of the services for the building in terms of electrical, heating, cooling, all of that stuff. Essentially making the buildings suitable for the people who use them. So we have also lighting, acoustics, utilities, and all sorts of other specialist groups involved in that process. So we build things like this. So this is kind of what we design. This one is some duct networks and some piping networks. But I just move on quickly. So in terms of the design stages, so we start off with an outline design. So we find out the requirements, we analyze the sustainability credentials, do some simulations, and then we move on to the detailed design, and then we move on to the build, which is usually done by another contractor. And then finally the in-use stage is where so we're looking at the performance and management and maintenance of that building. And in terms of software which we use predominantly Autodesk Revit in the first stages. But we also use some other 3D packages such as Rhino, as well as energy modeling packages such as IES and Energy Plus. So this is Revit. This is our main tool, which all of the people involved in the project use, so the architect and the structural engineer. So we all try to bring our models together in this environment and federate our designs. So the technical bit. So in terms of use cases, we come up with several. In terms of so we want to capture the early stage design requirements without spreadsheets. So we heavily rely on previously on spreadsheets and to capture all that information. So in terms of all the calculations that are done or exist on different spreadsheets, but you want to bring it all together into one environment. We also want to integrate the modeling software which we use. We want to make it easy to generate schedules of building components and Power BI integration. We also want to reuse the existing data for new projects, as well as feeding back that in-use data to early stage design. And the example that I'm going to show you today, which is a facilities management type web portal showing building services with sensor data. So that is the architecture. I'll just show you a quick video of what it does. Okay, so hopefully you are seeing this. Wait out if I press play. So what happens is the user walks into a space like that. So it queries the graph, it finds some information about that space. So in this case, it's all of the sensors. And from a separate API, it gets the data from those sensors. I'll show you that in the diagram in a minute. So as well as sensor data, here's the graph stuff. Let's find a good one. So what happens is the user clicks on the button, and in this case, it highlights all of the air paths back to the air handling unit on the roof. So you can just click through that, and it highlights it in the model in the background. So that's air paths. So we also have electric. So that's air paths again. So that's more air paths. We have electrical in here somewhere. Definitely have lighting. Anyway, I think that you get the idea of how it works. So let's go back to the screen. Right. Back in the screen. Okay. So in terms of the architecture that makes that work, so most of the services are hosted in Azure. So we have a function endpoint, and we have HTTP and a Bolt endpoint. The Neo4j instance is in a Docker container, and the HTTP website is served from Node.js. And to make it all work in Azure, we have a router, an Nginx router. So, and then the other important thing is the actual 3D geometry, which is all served from Autodesk Forge. So we're using the Autodesk Forge platform to serve the geometry as well as the 3D viewer which they've built. So essentially what happens is the models that we build in Revit get uploaded to the Forge platform, and then that serves an optimized file for viewing in the web browser, as well as on this side, we parse the Revit model, and through the Bolt protocol, we populate the Neo4j database with all of the model information and all of the relationships. So I think that the next slide that's the video. Right. So this was kind of the sequence diagram of what happens when you walk into that space. So before that, it's already served up the model. So in order for it to know where to get the model from in the first place, that is also served from Neo4j. So that has a unique URN which to the model on the Forge platform. So when they actually walk into the space, so I've done a kind of a hybrid for Bolt and GraphQL endpoint here, because when I was building this, I was just getting started with GraphQL. So it gets all of the sensor data from the GraphQL, and I was just going to show you where that happens in JavaScript. So on enter the space. So it already knows which space you're in, which it does through a ray tracing method. So it knows the name of the space, and it sends that space for GraphQL.
Will, can you hear me?
Yes.
Can you increase your font size a little bit?
Yeah, hang on. Why isn't it zooming? Yeah, I'm trying.
Perhaps just Control Plus or Command Plus or something like that too.
Yeah, hang on. Right, there we go. Is that better?
Thank you. Much better.
Yeah, let's try one more. There we go. Okay, so it already knows which space you're in for the ray tracing method, and then it's a GraphQL query to our GraphQL endpoint. So it gets the space, and here is all of the sensors, the sensor data about that space, which it then renders in the panel on the right-hand side that you saw with all of those line graphs from the sensor data service, which was a separate service. Let's go back. Don't play that again. No, yes. So that's this service here. So it sends an HTTP request and gets all the sensor data back and displays it in that panel. Okay. So where was I going to go to next? So I was going to show you the C# codes that we've written to essentially analyze the Revit model and push it out to Neo4j. So let's make sure I get the right one. Yes, that one, Revit to Graph database. So hang on a minute, that's the next one. There is that one. That's that one. Okay. So we have a series of parsers, and let's start from the top. And each of those parsers look at the building, and through the logic that we've built, build an in-memory graph initially, and which is just a C# data structure. So that once it's done that, it goes through each of those nodes and finally pushes them to the database. So for each node, so this is when it pushes the node in, it returns the pending node. So it doesn't actually write it to the database at this point. It just says that it's accepted that node and gives it an ID. And also some constraints on that ID, so it ensures it's unique. So that it does that so that you can relate. So the order that isn't implemented. So the order in which you add nodes and relationships doesn't have to necessarily match. So you can add in a node or add a relationship which isn't related yet. Oh, actually, that's not quite right. Yeah. Anyway, so you can add in. So once you've added all the nodes, you add in the relationships, and then so it just adds that cipher query to the pending cipher queue. So then, and this is the final bit where it actually commits it. So using the driver session, it dequeues everything from the node stack for all of the nodes that need to be pushed, and then it does the relate stack and pushes all of the relationships into the graph. I think that the point I was trying to make earlier is that it needs to push in the nodes first before the relationships, so you're not trying to relate nodes which don't exist yet in the database. Okay, back to the slides. So what was the schema that we chose for this? So this is what we wanted to do was abstract the model from design. So the point being is that from the design can be related to multiple elements in the model. So that's kind of a method to achieve versioning. So we could have two different versions of the model which would relate to the same design. So in that way, we could detect changes to the model. And also associating, so that two different models for different purposes could relate back to the same element. So in terms of a space in Revit could be related to a space in another software package which we use called IES. So the idea is that they would be able to send data between each other because they would each know they were looking or doing calculations on the same space. Okay, and this is the schema we chose for duct networks. So it just models the airflow. So it goes from a duct to a duct transition to another duct, all of that kind of thing. But also from the terminal to the space, it's important to capture that relationship because we want to know how much air is being pushed into or out of a space. It's also I haven't illustrated it, but it's also very similar for liquid flow. So we've also done this for pipes. So this is kind of what we get with a query like this from our graph database. Okay, and also for electrical. So we have, for electrical services, we have these things called DB panels. So all of the DB panels have circuits on which connect to another panel and to another circuit to the sockets and light fittings, which are called loads in here. So in our graph database with a query like this, we get a structure like this. So all of these blue nodes are circuits, and all of these yellow nodes are things that we have connected to the circuits. Okay, and the other interesting thing that we wanted to do was to extract the geometric features. So this essentially was to allow for heat loss calculations to be achieved directly in the graph. So you wouldn't need to keep analyzing the geometry to do that. So what we would thought of is between any space, there would be a surface, and that surface could be on a wall, it could be on a door. I haven't put it in here, but it could be a window. So then the idea with a query like this, we can find out all of the bounding surfaces of a space, and we find out what surface that is on, and information let's go back. So information will be included on the thermal coefficients in terms of the walls and the transmittance factors of windows and all of the things that we need to do those calculations. But I also think it would be great at some point to capture the full geometry in the graph. So in terms of boundary representations or mesh geometry. So that's for future projects that I'm going to try and do. So essentially, if we could do that, then we wouldn't need to transfer different files between applications. We could transfer it all via the graph. Okay, next one is the IoT stuff. So this is right at the other end of the scale, where we're looking at in-use data in buildings. So the point in this is relating in-use data back to the original design. So in this case, we have a space and we have a sensor sensing that space. It could be CO2, humidity, all of these things which we gather about spaces. But as well as spaces, we have the air handling units and other bits of equipment and sockets which are attached to the space. We all have sensor data. This is all coming from those things, and that's all related in the graph. So we can use that data, hopefully. I mean, I haven't done any yet, but we're looking at using it for machine learning in some way. Okay, and also I mentioned earlier detecting parameter changes. So where we have that abstract and model element relationship, we can run a query like this, which finds any differences in the parameters between these two and creates a change request so that in the original application, they can choose to pull in those changes and update their model elements with changes from elsewhere. Okay, so there's loads of things that you want to do with this. So we can calculate air paths back to rooftop equipment, air handling units, shortest, longest air paths, pressure loss, and other calcs. Shortest path along cable trays, that's useful for when we need to calculate lengths of cables when we connect between two different DB panels. And the surfaces and paths of adjacent spaces, which I think I just mentioned, and also creating taxonomy and classifications from the existing nodes, quantitative takeoff and other schedules. I was just going to show you the calculating heat losses between spaces and how we've been doing that so that's the end result. But to get there, we first set the temperature outside, in this case 18 degrees, and then we set the temperature inside the spaces to say 21 degrees. And then through the boundaries information that we have built from the Revit model, so this was the geometric feature extraction stage, we set the temperature delta of the surface, which is the outside temperature, well, the surface on one side minus the temperature for the surface on the other side, or space. So that just returns all the sections. And then finally, to calculate the actual fabric loss, we take that temperature delta, multiply it by the area of the surface and the heat transfer coefficient of the thing that the surface is on, and it turns the fabric loss. So then for each of these, so that's the fabric loss. And then I think this one's just visualizing that information as we saw just briefly just now. So then each of these surfaces has data which indicates the amount of watts that are passing out of that space, which can be used elsewhere. Right. So some notes about issues that we had getting this working. So in terms of container, so we used Azure container instances, which we kind of regretted because it didn't work too well. So the only way to get it working is with an exact YAML file. So I was going to show you that briefly. It looks a bit like this. It's obviously not particularly useful in here. So I am going to post it up to my GitHub account. Anyway, it's not on there yet, but I'll put it on there. And so if you're using Azure container instance and you're using Neo4j Community, essentially there's no backup facility, because when you stop the container, it completely kills all the data. So there's no way of running a separate commands to back up that data, and there's no in-use backup facility for Neo4j Community. So I did try hosting the data directory in Azure file storage. That kind of worked, but then it stopped working with file IO errors after about 10 minutes. So that's kind of a non-starter. But the plugins directory and other directories, read-only mappings, they do work fine. In terms of the routing, you cannot route from a load balancer to a container instance. So you have to use another VM to do that, or you can use the firewall, but that's quite expensive in Azure. So I think it's probably better to use a virtual machine to host your containers. Also, or Kubernetes, if you're brave enough. I tried that, but it's complicated. It's pretty complicated to set up, and I quickly realized that I didn't know enough about what I was doing to actually do that. And also for SSL, we set up certbot in another VM, which copied certificates over to the certificate location for Neo4j containers. And also a small thing that in Azure, at least one VM must be attached to a load balancer for it to be given a public IP. That's one of the issues that we had, waiting for ages for an IP when nothing would ever come until we brought up a VM. I was going to show you a quick example of using Node-RED. Let's just have a look at the time. Yeah, I'll probably show that quickly. So all of this does is it sends a graph. So it's actually exactly the same GraphQL query that we saw earlier, but it's in Node-RED. So it's the same thing. So what's great about Node-RED is it enables you to get up and running without having to do too much coding. But it might require a little bit of JavaScript to get some of these nodes working in terms of manipulating the payloads that come out of the GraphQL queries. Okay, and the other one I wanted to show you was a Power BI connector. So I know there's one available now actually on GitHub, which you can load into Power BI. But before that existed, I built one which is just from a template, which is just a query rather than a connector. So that example is up in this GitHub location. I won't go into it because you can just go in there. So what are we working on next? Okay, so this is our grand vision. So at the moment, all of these applications communicate by their own individual file formats. There's a little bit of interoperability, but mostly they have their own bespoke files. There's a little bit of interop between the applications themselves, but essentially there's no relationship between the data that Revit has and the data that IES has, or the data that's in Excel or Rhino and Grasshopper. So we see the Neo4j database and a GraphQL schema as a way for each of these applications to communicate the building designs and to all communicate through a single design nucleus, which also enables other services to use that data. So as we saw earlier, the IoT data that's available, our aspirations on using AI, analytics, and the other Autodesk platforms that they have, like BIM 360 and Forge, as well as mobile apps and other web portals and facilities management software. So with a single schema, we hope to use that to be able to learn from the existing data and feedback that into new projects and other existing buildings. And another thing that we're looking at the moment is Kafka. So that's to send messages between the apps so that they know that there's new data available for them to use to run some more counts or to update the database with whichever whatever they need to do with it. So it could have a service which does duct calculations and air pressure loss calcs. So when you change the graph, it would know to update that. Okay, so to make that work, we have been using GRANDstack. So one of the great things about GRANDstack, as I think we've heard today already, is that automatically generates the types, mutations, and queries, which is brilliant. It saves us having to write all of that stuff manually. And another great thing that we've actually found is that it can combine multiple GraphQL files. So what we've been doing, if I can find the right one. So what we have is several GraphQL files, and there's a bit of duplication in each one, which essentially adds additional features to the types, additional fields. So we have a single space, but we have another one with extended space information. So the idea is that depending on the design stage or the requirements of the building, you can add or remove different features from the graph. So essentially, it enables the design to progress organically, as well as the data behind it. So to make that work, it's really easy. We just use the merge type methods from the GraphQL merge GraphQL schemas package. So that works really well. But we did find that we still needed to make a few of our own mutations to enable some special cases. Okay. Another great tool is GraphIQL. So what we love about this is that it has automatic introspection. So when you start typing, you get IntelliSense, which tells you what is parameters you can add. So what parameters are available from your database. You still see my screen, or has it gone over to the? Yeah. Anyway.
Yep.
You still see my screen, yeah?
Yes, all good.
Cool. So just things like that. So other things that we've done. So in terms of finding space contents, so for this space, we can find all of the elements in that space. And there are some other things in here as well. Okay. Okay, so the next bit I wanted to show you was the GraphQL C# library that we're building. So we've kind of only just got started on that. Let me just find it. Not that one. Yes. So at the moment we are building the introspection API part of it. So the problem that we have with the previous one is that it just filled the database up with a million of parameters, and we didn't actually need all of them. So by using introspection, we can find out which parameters the database actually wants, or we actually need. So we've actually used dynamics to do this. So the idea behind that is to reduce the amount of ORM classes that we need to build. So I suppose it borrows a bit of technique from JavaScript. So the reason we can do that is because the GraphQL query gives us assurances over the data that we're getting back. So if it's not in the right format, it will give an exception at the database layer anyway. So that's kind of as far as we've got with that one. So back to the presentation. Yeah, so as I was saying, we can use dynamics over ORM concrete classes because of the GraphQL assurance. And yeah, as I was saying, GraphQL introspection tells us what fields are available at runtime. And I suppose the other thing you might have seen briefly is we were using the description part of the GraphQL spec to add some additional metadata. So we wanted to be able to, I won't go into it, but we wanted to be able to say for any particular field what the units are. So as well as the data type, we need to know like if it's meters per second or all of that kind of things, which are useful to have. Okay, so that's it. So thank you. So we'll go on to the questions. So these are the Hunger Games questions. And let's just have a little read through. So I've got some questions here. How big is a graph for a building? Is that in terms of the number of nodes? Where we can have a look. So the example building that I've used for this only has 8,000 nodes and 23,000 relationships. So I have tried it on some bigger buildings, and I think it was in the region of 100,000 nodes and 500,000 relationships. I think it might have been a bit more than that. But the database performed really well. The thing that didn't perform too well was the algorithms that we used on the Revit side to push that data in the first place. So there's definitely some room for improvement on that side. So the question is, another question, do we use the 3D spatial coordinate functionality yet? We haven't used that yet. I've seen some classes today which seems to suggest that we should be using it. So I'm definitely going to give that a go. So at the moment, all of the geometry information is as a separate X, Y, and Z parameters. One thing that I'm not quite sure on yet is how we would use the 3D information or 3D points in GraphQL. So I'll have to look at that. And do we have any Node-RED 4? Do you use Node-RED 14? Do we use the Node-RED Neo4j integration? I have seen that. I did try it initially, but the reason we're using GraphQL is we wanted to have that abstraction away, so we didn't want users to have to write Cypher queries. So we're hoping that they would just be able to use the existing GraphQL schema. Okay, and we have another question. How long have I been spending on this presentation, and how many have been involved in this project? Okay, so I've kind of been working on this for maybe a year or two. So I first did a presentation on it for Autodesk University last year. So that was when I first kind of started. And in terms of who's on it, it's just me. I'm the only one at the moment who's working on this, but it is actually gaining quite a lot of traction here at Hawley. So we're hoping to get some more resources and more developers involved in building it. I just check the chat. Any more questions in there? Okay, so it seems that spatial support is still coming in Neo4j. Excellent.
In the GraphQL indication. Thanks so much, Will. This was truly impressive, and you're probably a real 10x coder. So
thank you.
Good work.
Thank you.
Have a great evening, and thanks a lot for your presentation.
No worries. Thank you.